Hi, welcome to recap lecture number 2. In this lecture, we're going to go through implicit differentiation and then a little touch on related rates, as that is one of the main times we used implicit differentiation. And then we'll move from that into the derivative testing that we do to find extrema and points of inflection and so forth. Okay? So implicit differentiation is what we use when solving for y is impractical. So we don't have an explicit definition of our function. I'm using a different laptop right now, and I'm writing with my finger. I don't know that my handwriting is any worse than it usually is on a tablet. So thank you for putting up with my really, really bad handwriting. In this case, finger writing. I feel like a child in the sand at the beach. Anyway, so we use implicit differentiation when it doesn't make sense or it's not possible or it's not necessary for us to get y equals 1. You can see in my first example, y is mentioned in 2 different places in this relationship. And so even though we could manipulate this and make it, think of it as a quadratic in y with x as one of the inputs, it just would be awkward to use quadratic formula to isolate the y and then take the derivative. That's not really necessary. You can just go at this thing with calculus. So our first term's derivative would be 2x. Then I'm going to think of the next term as being negative 5 times the product of x times y. And so I'm going to think of um, I'm going to think of this as negative 5 times the product of x times y. So to take the derivative there, I'm going to think of the product rule. So first, derivative of second, plus second, and then the derivative of the x would just be 1 because we're taking the derivative in terms of x. X is the independent variable. And then we've got 6y, and dy dx because y is thought of as a function of x. And then the classic place to make a kind of thoughtless error is to not have a 0 there, to write a separate. Oops. And then after that, what we would do is to take all the terms with dy dx in it and leave that on one side and then move all the other terms to the other side. So we'd have negative 5x, and we'd also have positive 6y. That quantity times dy dx is going to equal the other terms that do not have dy dx moved over to the other side. So negative 2x and positive 5y. I do not understand why these little boxes keep showing up. Maybe one of you can explain that to me in class. And then we're going to just isolate the dy dx term. So dy dx equals, and then this guy from the right side divided by the quantity from the left side when you divide. Okay, and that's a perfectly fine understanding of what the slope of this function is at various points. Notice that the inputs on this function involve both x's and y's. So if we wanted to understand what was happening, in terms of increasing or decreasing, we would need to know information about coordinate pairs, not just about x's, not just about y's. All right. On here, using implicit differentiation, this is a problem that we would not have had when we studied this the first time because it involves the derivative of e to the u, which we did not at that point know. But here, now we do. So we will just go at this with calculus. We don't have to try to solve for the y, get y by itself. Possible in this case, y is just there in one place, but not necessary. Why would we do more work? So we'd have e to the u times the derivative of u, and the derivative of cosine is negative sine. And then we'd have the derivative of e to the u times the derivative of the u, so that would be cosine of y. Also a dy dx there, because y is our dependent variable. We didn't need to do that back at this stage of the problem because x is our independent variable. Seriously, these boxes are killing me. Anyway, and I just don't even know what to do. And over here, we've got 0. Okay, so then our whole task would be to isolate this single dy dx, which is just a tabular algebra. So dy dx equals, we'd move this term to the other side by adding it over. It's my own personal preference to put the sign part in the front. just so it's not confused with being an exponent. And then this other part over here would end up being the divisor. So cosine of y, and then e to the sine y. This was actually a question from an old test of mine. And I remember that students on it accidentally looked at this portion and wrote tangent. Why wouldn't that be okay? I hope you thought about the argument here. So sine of x and cosine of y, that doesn't make tangent. Okay? Okay, oh, one more question. There's another question here about, it has this relation. It must be some kind of conic section. That would be my guess just glancing at it. So find the coordinates of the 2 points on that equation where the line tangent to the curve is vertical. So the first thing to interpret about this question is that a line is vertical. A line that is vertical has undefined slope. So when we find the slope, we want to think about what would make the slope undefined. So first we'll take our derivative. It's okay, I'm just going fast through here. Again, it's just so weird. I know you guys can't really appreciate how weird this is by writing with the finger. Very strange. Maybe not to you, but to an old folks, to me, yeah, it is. Okay, then we isolate the dy dx, and we would get, let's see, that would move to the right, so negative 2x, adding the 2, and then dividing by the things that were with the dy dx, that were like coefficients of dy dx. Okay, so there's our slope, and we want to think about where that slope is going to cause a tangent line to be vertical, which means this part has to be equal to 0. Again, with the box. Seriously, folks. Okay, so we're going to think about where that bottom part would be equal to 0, and that bottom part will be equal to 0 if y is equal to negative 2. So that's not quite enough because it is asking me to find the coordinate. Notice that's plural, and this is just a coordinate. So we need to substitute negative 2 in this y and figure out what x is going to equal when y is negative 2. So let's go about doing that. So we're going to substitute in at the beginning. You would have x squared minus 2x plus 16. Yes, I'm remembering the question right. 16 minus, I should really just stay up there for a while. Oh, I have it on a piece of paper. Minus 32 plus 1 equals 0. Okay, so you plug negative 2 into all of those things, and then tidy up, so you'd have x squared minus 2x, and then combine like terms, minus 15 equals 0. So factoring here would give us two solutions. So we have the solution, the ordered pair of 5, then negative 2. And we have the solution of negative 3 and negative 2. The negative 2 is from the y coordinate we found already. So these are the two locations where the tangent line goes vertical. Okay? All right, let's move along and let's talk about related rates. So related rate is an area that you guys probably remember with such great fondness as being story problems where we use implicit differentiation. And the good news for you is that I haven't seen, in the last few years, I have not seen related rates mentioned in pre-response questions, which minimizes the point value for you all on your exam. I would think my money would be on seeing related rates tested in multiple choice questions, probably on the non-calculator part, and keep the numbers nice and simple. Just ask you some real basic ones. So I put a box here just kind of reminding you of what the steps are in doing a related rates question, and then I just gave you a basic one. This is the kind of thing I would expect to see, just multiple choice format, it would be my guess. Suppose that an inflating balloon is spherical in shape and its radius is changing at the rate of 3 centimeters per second. At what rate is the volume changing when the radius is 10? So we need to identify the things that are mentioned in the problem. I see mention of radius. I see mention of volume. And so I know that I need to have something that kind of connects those two things. It also mentioned that the balloon is spherical. So I want the volume formula for a sphere. And then I'm going to differentiate that because I want to know something about the rate at which the volume is changing, and so that means dV dt. Notice here we are differentiating with respect to t. T is not actually, or time is not actually an explicitly stated variable here, but radius is affected by time, volume is affected by time. So think of volume and radius as functions of time, which means that every time you derive, you have a chain rule situation. Those are both determined by time. Time is the independent variable. Over on the right side, we would have 4 pi r squared, and then the r dt, thinking of radius as a function of time, therefore chain rule applies. And then we go back up into the question if we can. There we go. And it said the radius was changing at a rate, so that's the RDT, of 3 centimeters per second, and we want to know the VDT when R is 10. So we just substitute in. Notice that our substituting in happened after the derivative. Only things that can be plugged in before the derivative are things that are always true 100% of the time. Otherwise, you substitute in at the end. Okay, so this would be 1200 pi centimeters cubed per second. And those units came about because of what's mentioned in the question. Centimeters are mentioned in the question, seconds are mentioned in the question. And I'd say centimeters cubed because we're dealing with volume. All right, the last little thing to go over is curve sketching and derivative testing. So I have this whole list here, and one of the things that I would like to point out and literally highlight is this series of sentences in here offer up a nice way for you guys to write justifications. So notice that these sentences do not say it anywhere. They do not just say a function, they say the function f or the second derivative f double prime. They use labels. These are great ways to write your justifications. Excuse me there. So just bear that in mind. I feel confident that everyone in our class knows these sentences, knows them to be true, but sometimes the wording that you guys offer up is a little, so we need to make sure we're referencing specific things, right? If the first derivative f prime is positive, that means that the function f is increasing. And sometimes if we leave out this, if it, let's just say here, if it is positive, then it is increasing. Oh my God, that just gives me kind of chest pain, okay? So let's not do that. Okay, let's try to be a little bit smarter than that. Okay, we are definitely smarter than that. There's a lot of capability for us to be good about this. Okay, the next section of sentences discusses how to find relative and absolute extrema. And statement 7 discusses point of inflection. Remember that for point of inflection, the key, the student mistake or the typical kind of mistake when you're first learning this is to just jump to conclusions and say that if the second derivative is 0 or undefined, boom, point of inflection. And you actually need to look for a sign change. Sign change, sign change, sign change, okay? So in order to move something from being a potential inflection point to actually being an inflection point, there has to be a change in sign in the second derivative. And then the last part down here, this requires some studying, I think. This is the second derivative test for extrema, and there's 2 parts to it. You have to first know that you have a critical number, which means that the first derivative is 0 or the first derivative is undefined. And then you need to look at the second derivative information. And this is the one that it really makes sense if you think about it. If you know you have a shape that's concave up, the second derivative is positive, and you have a critical number, that means that the point you have is that point right there that I tried to indicate. And then the flip of that is literally a flip over, right? If you know you have a concave down section of your graph and you know you have a critical number, then that critical number must be at that max point, okay? That's the gist of that. I hope that you can just read through that. You need to have the ability to write justifications, not just be able to figure it out. And also remember that readers of your tests do not look at sign charts at all. That doesn't mean you shouldn't make them. You absolutely should make sign charts because it helps you to think. But you need to take the information from a sign chart and write it in a sentence that is a strong sentence without any ifs in it. Okay. The last thing that's in your notes packet is a problem. I'd like you to try, pause the recording, try the problem, and then we'll come back and check it together. Okay, here's the problem that I hope you just tried by yourself. I really hope you did. We did this problem actually. This is out of an old packet that we had together. And so we are asked to find extrema. So the first step is finding the first derivative. And this is me making the first derivative a little bit easier to deal with. And the next step is the one where there's sometimes is a little bit of algebra panic. You want that first derivative to equal 0. So if you put in a 0, you can then move one of these terms that's in red to the other side of the equal sign. And then everything's lovely from there because you cross multiply and boom, no more radicals, which is great. And then and then, you know, without the radicals, then it's just a nice little simple quadratic to solve. Oh my goodness, this won't scroll. There we go. Nice little quadratic to solve. And then you do your sign chart, which again, they are not going to reference as in terms of grading you. But you know that when the derivative changes from negative to positive, the original function has a minimum. And, you know, conversely, when the derivative changes from positive to negative, that means the original function is going from increasing to decreasing. Therefore, you found a max. So we would want to write up here that our increasing, decreasing intervals are these. So negative root 2 to root 2 is where we have the original function increasing, and then negative 2 to negative root 2, and positive root 2 to positive 2 are both sections on which the original function is decreasing. And then our places, the x-coordinates where we have extrema, we have a min at x equals negative root 2. We have a max at x equals positive root 2. I hope this has been helpful and not too painful in terms of length or time, and I will see you in class.